Okay, all right, now we're rolling. Okay, here's another poll, I think, about which section, if you have a preference. Still trying to get some feedback from you, so it's just not me doing things you guys hate anyway. Okay, a lot of chapter 17. I think you can pick more than one. Just please try to avoid picking all of them. Okay, cool. Okay, so I'm gonna, we got one more person. Okay. Okay, titrations. That's what it looks like from the majority of people, so we'll start there. Which one? So titrations and buffers. Oh, we got the monster problem here. We got the big guns. Where is it? Okay, here it is. Share. There you go. All right. I think I'm just going to start talking about it. If you feel free to just ignore what I'm saying and work it out on your own, but I think it's probably. Where's my pen? Sorry, I had a pen over here. Thought I did. Oh well. Okay, we have this problem right here. It's like the problem he suggested a long time ago, 1735, where he gives us a titration and has us evaluate the pH at a bunch of different volumes. So I'm gonna write down all the stuff. 10.0 milliliters of 0.300 molar NH3. Oh, I forgot to give you the KB. Hold on. So the KB NH3 is 1.8 times 10 to the negative 5. There we go. Okay, we're taking that ammonia solution and we're titrating it with 0.200 molar HCl, right? Yep. We're doing a bunch of different volumes. All varying. Okay. Let me write down. Oop. Don't know what that sound was. Interesting. Is it doing? Sorry, lost my train of thought. Okay. Okay, people write this down. Or they have it somewhere. Take a picture of it. Maybe. Because I don't have the space to write. I don't at least write the volumes down. I don't have the space for it on my board right now, so I'm just going to write it down as we do it. Okay. All right, I'm going to stop. Okay. So the first one The first part was when we added 0 milliliters of that. Okay, and then does everyone see that this turns into a chapter 16 problem when I have none of this? I'm just asking you for the pH of NH3. And then I told you that the KB. Right. Okay, so could everyone find the pH of that if I asked you to? So everyone, I'm asking you if you can find the pH, or should I work it? Work it. Okay. Sweet. That's fine. Okay. All right. So finding the pH of this, so we got to write our acid-base equation, right? So Kb, right? This tells me it's a base. I don't know if you can see that B. Do we leave it as Kb or change it to Ka? Excellent question. Okay. All right. So this, right? This Kb is for NH3. So we leave it as Kb for right now. Abby, I think you're thinking about something we'll do later at the equivalence point, which is also good. You're thinking ahead. Okay, so the first thing I got to write down my equation. So NH3, right? And then for all of our acid-base things, we added it to water, H2O. Hopefully it's not too big. Liquid goes to, okay, remember it's a base, so this is going to be accepting my H plus, so I get NH4 plus aqueous, I guess, yeah, plus OH minus, right? Okay, insert ice table song here. I'm too lazy to pull it up. But now we do our ice table, okay? So ICE. All right, get rid of this. Don't care about liquids in our ice table. Right, so initially we start off with 0.300 concentration, 0 here, 0 there. Right, since we have zeros, we need plus x, minus x. So I get 0.300 molar minus x, x and x. All right, no one's lost. Let me know if you're lost in the chat, or raise your hand or something, and I don't know if you can raise your hands. Maybe you can, I don't know. But yeah, just let me know if I say something that confuses you, and I'll stop and explain it. Okay, all right, now we have, right, our equilibrium values, so we can set them equal to our Kb, right? So we know that from our equilibrium expression that Kb, or I'm just gonna write the number, what is it, 1.8 times 10 to the negative fifth equals 3.300 minus x over x squared. How come we didn't do the limiting reactant thing first? It's because you have 0 milliliters of your HCl, right? So there is no limiting reactant to do. Well, I guess you could, but it'd just be, nothing would happen, right? You would do your, so what you're talking about is your NH3 plus your HCl gets you your what was it, NH4 plus Cl minus, right? That's what this is the limiting reactant we would have done. But this would have been what is that? 0.003 moles, right? And then 0 moles right there, 0 moles, and 0 moles, right? And so you would just, the limiting reactant here is this, but it's 0. So -0, -0, -0, -0, -0. So it's just, you would get back to there essentially. You could have done it. It would have looked like this, but I just realized though, oh, this does nothing. Okay, did I answer your question? Thank you, that makes sense. And why do we have OH minus on the right side, not H plus? Because this is a base, right? This is a base. Base. So the base, it accepts a proton. So you can always think of H2 as HOH. Okay, thank you, cool, yeah. Right. So yeah, always pay attention, right? Well, ammonia is a thing that doesn't look like a base, or yeah. So just pay attention to whether it's Ka or Kb, and then you'll, in your thing, if it's Ka, if it was Ka there, then I expect the H3O plus or H plus. But since it's Kb, I expect an OH minus. Good questions. Where's my eraser? Here it is. Okay, don't need that. Okay, so here we got our equilibrium stuff. Okay, remember a long time ago, well, I don't know how long, depends on what you think is long. Here we have, okay, this thing is times 10 to the -1, right? If I wrote it in scientific notation. This is times 10 to the -5. So I'm gonna make my x a small assumption right here, right, to make my math easier. Right, get rid of that. So I'll calculate x now. What is my x? Where is my calculator? Ice baby stuff in my head. It's my own fault. I got 2.32 times 10 to the -3. Well, I guess it just for 2.3, right? Sig figs. I'll try not to be lazy with my sig figs here. Multiply, right? Yeah. Multiply by this, right? Multiply by that, and then take the square root. Correct. Okay. Now we have this, right? Remembering that, oh, well, what I need to do now is check to make sure my x is small assumption is right. So now I take this, so 2.3 times 10 to the -3 over my initial amount, so my 0.300 times 100. And so that's 0.77%, which is definitely less than 5, so we're good. So this guy's good. Right, don't forget to check it. You might take off a point if you don't. Okay, almost done. Here we go. Okay, so now I can get, this is my OH minus concentration, so I can get POH. And what is that? Going to be negative log of my 2.3 times 10 to the -3. And so POH is where's my log button? this? 2.6, yeah, 63. And so my pH is just 14 minus that, which is going to be my 11.37. 2.63. Okay, yes. Cool. Yeah, don't trust my math. I always like to add zeros when they're not supposed to be there. Is that right? Go over here. Okay. I see I made a mistake when I made the PowerPoint. Cool. Same. That's what I got. Awesome. Sweet. Questions on that? Like this is basically kind of, there's another type of question in chapter 14 that might be a little tricky, but this is kind of what chapter 16 was, right? Just giving you something and asking you for the pH. All right. Okay, I'll give you, we're all good on this one. Got it, thanks. Awesome. No worries. Okay, not seeing anything. I'm gonna guess we're all good. All right, I'm gonna erase it and we'll do another one. Next one, hopefully, let's see, okay. Okay, erase all this. Changing our volume. Now we have 10. 10's the next one. 10 milliliters. Okay. All right. Get rid of this, don't need that. Okay, now we have 10 milliliters. So now we actually have to do that limiting reactant thing. I think Anastasia mentioned it earlier. I'm sorry if it wasn't you, or if it was someone else and I'm not giving them right credit. Okay, so now we got to do our limiting reactant thing. So NH3, right? It's going to react with my HCl. And it's going to go to NH4 plus my Cl minus. Right. Ooh, excuse me. Okay. So now I need to calculate the moles of these two things, right? From my, is this where you can just say H plus or no? Yeah, you could just say H plus right here if you wanted to. So if you wanted to put just like get rid of your Cl and just say H plus, because it's kind of a spectator, right? That's fine. Just remember that this H plus came from your HCl. So when you calculate moles of this, it's the moles of your HCl. Yeah. So you can do that, or you could just put Cl. Right. As long as your proton is moving to the right spot. Okay. Then you just calculate moles of these two. I'm just going to do it. So let's see. So I have my 0 times, I'll write it, 0.0. So we have our 0.010 liters times our 0.300 molarity. And that gets us what? 0.003? Right there. And then we have 0.010 liters times molarity, and that gives us 0.002 moles. Oh, it's terrible. It's terribly out of angle, but that's okay, hopefully. So 0, I don't really care about this. Okay. Okay, so we do our limiting reactant thingamajig. And so this is a limiting one. So we subtract 0.002 moles minus 0.002 moles minus or plus, right? Plus on this side, 002, almost messed up. So you get 0.001, 0.002 moles. All right. Okay. So we have our base, a weak base, and its conjugate part, right? So who knows what we got? What we got here? Does anyone remember the name? Starts with a B. Yes, buffers. We have a buffer. Yes. Right. That means we can go to our Henderson, Hasselbalch, or Hasselbalch, Hassel, whatever. Okay. Well, hold on. Why do we add 0.002 to NH4? Because it's like a it's kind of like your equilibrium, but it's not. So so here on this side, this is my limiting reactant, so I'm gonna lose 0.002 moles of that, right?
Yay.
Oof. Okay. This person scared me. Okay, so I'm losing this. This is all gonna go away because it's the limiting one, so it's gonna run out first. So I'm gonna subtract it from both of my reactants. But since I'm using up that much of this, I'm making 0.002 moles of NH4 plus, right? So you're losing reactants and you're gaining products, right? This is kind of like our X, you can imagine. Is that okay? Cool. Woo. Okay. What was I saying? Oh, Henderson. So we got a buffer, so we can use. How do we know it was a buffer? So you have your conjugate. This is a base, right? It's a weak base. Weak. And its conjugate acid are in a solution together, right? So you have two things, these two in a solution together, so it's a buffer. I guess technically you also needed the ratio to be 10, but we're just assuming that that's going to be okay. Cool. All right. Okay, and then you'll go to your equation sheet and pull out your Henderson, Hasselbalch, whatever it is, whatever it's called, plus the log of the base over the acid. And before I mess up that equation, where's my, oh crap. Okay, two questions. Why does Cl get crossed out? And do you subtract 0.002 on both sides because it's limited in the equation and is less than NH3? Oh, and could you just solve it like the regular ice table instead of using the equation if you didn't know it was a buffer? Yes. Okay. To answer the question about using a regular ice table, you could use a regular ice table there, right? You could do your NH3 plus it still be water, H2O goes to an equilibrium with NH4 plus OH minus. Could do your ice table thing. Just remember you need these in concentration, right, to put them in here. So if you do this, and if you do the ice table, just remember to divide by our total volume up there, which is 20 milliliters or 0.02 liters, right, if you put it in there. So you could do that, and it'll get you the same answer, more or less. Okay. So that's the ice table question. And then, so why does Cl get crossed out? And do you subtract 0.002 on both sides because it is limited in the equation and it's less than NH3. So I crossed out Cl minus because this is the, it's like a spectator, essentially. I don't really care what's going on here. So I'm not worried about keeping track with how many moles. It doesn't show up anywhere else, right? So I don't care what's going on Cl minus. And then I subtracted it on this side, yeah, because it's the smaller one. So when you're picking what's your X kind of, you look at these two, right? You look at these two numbers and see, okay, which one's a smaller one? So then you subtract the smaller one on this side and you add it on that side because that's the product. Okay, hopefully I answered both of those questions. Okay, thank you. Okay, all right, no problem. Okay, so we're not doing the ice table. We're just doing our Henderson-Hasselbalch. Okay. Lost my marker. So we need, first off, we need pKa. Ooh, excuse me. We need pKa, so we need a Ka. So I'm going to do Ka equals Kw or Kb, right? You'll get this equation in some way, shape, or form. So 1.0 times 10 to the negative 14th over 1.8 times 10 to the negative 16th or 5th. Oh, that's almost bad. Ka is, I think it's like 5.6 times 10 to the negative 10. I've used ammonium a lot, if you can't tell. Yeah. Oh, oops. Okay. Bam. So there's a Ka, get pKa from that, right? So negative log of 5.6 times 10 to the negative 10 plus the log. So here we can kind of be lazy. Usually you need to put concentrations in there. But again, since we would just be taking these moles and dividing them by the same thing, same number, we can just put the molar amount in there and get the same answer. So I'm just going to put moles. So my base is that. So my 0.001 over my acid, which is this, right? 0.002. So my pH, what do I get? Log of that plus my log of 0.001 divided by 0.002. Okay, I got 8.95. Yes, no. Does it make sense? Any questions about it? Got it. Good. Yes. I'll get on that one. Could you show me the question? Sorry, I was late. Okay, yeah. So this is what we're doing. I was looking at the answers. Okay. So here's the question real fast. Okay, I see your question you put in the chat. Just give me a second. I'm gonna put this up first. Here you go. Where do you, yeah, it is water. Yeah. So yeah, that KW will be given to you. That's the one for water. Okay, no problem. Alrighty, so we're going to, okay, gotcha, thanks. All right. All right, part C. Let's do part C. We're trucking along. What was I doing? Oh, I want to stop. No, I'll leave that up for now, just in case. Part C. Oof, I actually want to leave the Ka. So I'll be using it here, so I'm going to leave it up there since we already calculated it. 0 times 10 to the negative 14. 1.8 times 10 to the negative 5th. And then Kw, or Ka is 5.6 times 10 to the negative 5th. All right, 15 milliliters now. What we got? 15. Let me stop here. All right, so now we got our 15 milliliters. Oh, I should have left that. Rip. That's fine. Okay, put it back up here. So N, isn't that 5.0? Good call. Good catch. Boop. Good catch. Okay, NH3. I don't care about states. Plus HCl. It's going to be the same thing. Goes to NH4 plus HCl minus. Okay. So my moles of NH3 is going to be the same as last time. So 0.003 moles. Okay, we'll recalculate our moles of HCl. Right, so we get 0.015 times my 0.2, and I get 0.003 moles. Hopefully, if I did my, if I set up this problem like I wanted to. Right? Oh, you can barely see that. All right, bigger. 0.003. Okay, they're the same, so we'll subtract both of them, or subtract the lowest number, which is 0.003. Subtract, and then add it, so these are 0, don't care about that one. Add it to this side, 0.003. So I get 0.003 moles of this guy, and 0 of that, and 0 of that. Right, here don't have a buffer, we just have this left over. So now the question becomes, how do you find what's the pH of this solution? And again, right now, we're going to divide by our total volume. Why didn't you do anything with NH3? I am confused what you mean. Like, oh, like why didn't calculate it? I was just thinking it was the same as last time, so I didn't need to. Is that what you mean? So I still calculate, yes. Okay, so it's just, yeah, it's still 0. It's still 0.010 times my 0.3, right, to get my 0.003. Okay. Yeah. No, you're good. That's a good. It's being lazy with my work. All right. All right. So again, I need this to do our ice table stuff. I need a concentration. So we're going to divide by our total volume, right? Which is 10 plus 15. So 25 milliliters or 0.025 liters. Yeah. And that'll give me a number. Okay, what kind of problem would we divide the mole of NH3 and the HCl by the total volume? Okay, Okay, hold on. Let me do this number for okay. So what kind of problem will we divide the moles of NH3 and HCl by the total volume? So you'll never have in this type of titration problem, you won't have a instance when you have both of these left, right? Because that's the only time you would divide the moles by total volume if you had both of them left over. I'm thinking, and in this instance, I don't know of any. I'm not sure if there's any other problem that I'm thinking of where you get like you would do this and you have both of those left over. They're either one of them is going to be 0, right? So you're either dividing this one by the total volume by itself to do your buffer ice table thing, or you could just do the Henderson-Hasselbalch with the regular moles, or you're dividing that one by molarities like we'll do in the next part. Right? Did that kind of answer your question? You're never going to divide both of them by the total volume. Cool. All right, we got our molarity here for our NH4 plus. Okay, we'll do our quick little sorry, lost my train of thought. NH3 plus, no, right, NH4 plus H2O, ice table shenanigans again, NH3 plus H3O plus, doon. 0.12 molar, 0. I care about this guy. Minus X plus X plus X. 0.12 minus X, X, and X. Bam. Okay. 10 to the minus 1 again. 10 to the minus 10, right? So I can make my X a small assumption again. Let's do that. So I'm going to say that 5.6 times 10 to the negative 10 equals my X squared over 0.120. Again, I'm just ignoring the minus X from down there. So my X becomes something. Where is it? Oh, there it is. Don't forget to square root. 2.58 times 10 to the negative 6. Right? You gotta check it. So X, so 2.58 times 10 to the negative 6 over my 0.12 times 100 equals 10 times 100 is 0.0215, I guess, percent. It's less than 5. So good there. Yes. Almost there. And then finally, I do my pH, right? I can go straight to pH since I just have H3O plus right there. pH, it's a negative log that, so negative log of my 2.58 times 10 to the negative 6. So my pH is a number, hopefully. I got a different X. Oh boy. I might have messed it up. Sweet. Okay. Here's why. I divided by 0.02. Or the 0.12. The point, was it 0.12? I divided by it. So good job, guys. I'm trying to keep you on your toes. Uh, 3, 6, 7. How's this one? 3.0 times 10 to the -7. Huh? That one? How's that? No? Yes? I still got something different. 8.2 times 10 to the -6. Maybe I'm multiplying. Oh, hold on. Hold on. Oh, yeah. Oh, yeah. Times 0.2. Yes. Yes. Cool. Whoop. Yeah, 8.2. That's what I got. Cool. All right. Math part right there. That's my bad. So, I think yeah, that's exactly what I did. You're right. My bad. Told you guys should check my math. Master's engineering student over here. So 8.2 times 10 to the -6. I'm gonna assume whatever it is less than 5. Yes, I see no more. Cool. Negative log, negative. Okay, let's see if I can mess this up. 5.909. Sweet. All right, we made it, people. Awesome. Awesome. I'll make sure that's this over here. Yeah, cool. Okay, makes sense, right? Oh, and also remember that this, a little definition in case you ask you for it in multiple choice, this is the equivalence point, right? Because you have, well, your moles of acid equals your moles of base. So this is the equivalence point. Right. So could you have used Henderson-Hasselbalch like the last problem? No, I couldn't, right? Because, so can you see it right here, hopefully? So Henderson-Hasselbalch was pH equals pKa plus the log of my base over my acid. You probably don't care about this, but so if I tried to do it this way, this would be 0, and there would be 0, and the log of 0 is undefined. So you can't use Henderson-Hasselbalch because you don't have any base. Good question, though. Anything else before we do the last part, this titration thing? Okay, I'm not seeing anything. I'm assuming that's no. All right, I'm gonna erase this. Okay, I can be smart this time. And remember that I can still use this. No, that stays. Someone got in. Okay, that became 20 now. Ooh. Okay, now we just bumped it up to 20. Okay, so now I'm just going to change this. So now this is 0.02, 0.02. Did I do that? Yeah. So this is 0.004. Again, check. Okay. All right, so it's the limiting reactant thing. So I subtract the smallest one. So now I have this 0.003. This 0.03 is my limiting. So minus 0.003, minus 0.003, and then plus 0.003. Okay, so now I get 0.001 moles of this guy. Ooh, excuse me, and then 0.003 moles of that guy. Okay. So both of these are acids, right? That's an acid, that's an acid. So you got to remember that this one is a strong acid, and this guy, I'll put it, I don't want to put it right there, I'm gonna use that space later. Strong acid, this guy is a weak acid. Okay. So this part right here, I don't know. Again, I'm gonna use this later for calculation, but this is gonna control our pH, right? So this is the main contributor. I can just ignore this, which is exactly what I'm gonna do. I'm gonna ignore it. Right, because it's weak, so it's not going to contribute to the pH that much. But this one is going to control it. Okay. But again, I need concentration. Need a concentration. So divide this by my total liters again. So I have 30, so 0.030 liters. And so my concentration of that is math. Hopefully I'll get it right this time. 0.001 divided by 0.030 is, I got, so my concentration is, put over here, 0.03, how many 6 weeks? 3, I'll put 2. Okay. All right, and remember, since this is our concentration of HCl technically, since that's a strong acid, it's going to completely dissociate. So that's also going to be the same thing as my H+. Right. This is going to be my H+ concentration. I could just take the negative log of that to get my pH. pH, negative log of 0.033 molar. So my pH is going to be negative. I got 1.4748. Okay. How wrong is that, guys? Why didn't you plug it into an ice table? This is a strong acid, right? It's going to completely dissociate, right? Our ice tables are for our weak things. Remember? Oh, and then, oh, also you have to remember that list. Hold on. Right, strong acids, if you have a strong acid and it's going to completely disassociate. So its concentration is going to be the same as your H+. For weak acids, we didn't have that happening, so we had to do our ice table to figure it out. Is that ringing bells? Because if I wrote out the disassociation of that, so if I added that to water, H2O. So if I did it this way, I would get a straight arrow, right? Straight arrow because this is strong, so it's going to be H3O plus CO minus, right? No equilibrium there. Why are they the same again? Because they're the same because it's a strong acid, right? Strong acid. It's going to completely straight arrow, so it's going to completely break apart. This makes so much sense. I'm glad it makes sense. Right, you're tight. So again, he can't ask you this whole thing unless it's your entire test, right? Well, I guess he could. It depends on how mean he is. But I don't think he will. He'll probably ask you like a part. He'll be like, oh, here's a titration and I'm adding this much of HCl. And he'll ask you for the pH of that. But this problem just goes through all the possibilities, right? This is all the possibilities that a titration can do. So if you can handle it like this, like a weak base added to a strong acid, if you can handle the other cases, you have a weak acid added to a strong base or a weak base. Oh, hold on, I'm having a seizure. You have a strong base added to a weak acid, which is kind of just a flip. All the same thing happens, except just some calculations flip places. So this one is the opposite of the one that is in 735, I think. So in 735, you have a strong acid to a weak base, I think, maybe. Don't quote me on that. So those two will handle all your titration possibilities. Do we know what type of question will most likely be on the test? Probably a titration, right? Because titration is 16 and 17, right? It pulls ideas from both. So titration would be good. Solubility, right? Just anything from solubility, right? And then, the other two chapters, whatever's on your suggested problems from the other two. But yeah, let's speculate later. Let's do more problems for right now. So does this make sense to everyone? Is that right? Did everyone get that? Yes, awesome. Okay. Alrighty, so that's good. Oh, let me do my plug. Here's the sign-in sheet again. I don't know if everyone was here, but just in case, sign in there. Oh, please. Sign in there so I can send you the stuff. And if you don't get the stuff from me after this, just let me know and I'll send it to you. Okay, what's next? Oh, let me look at this poll. Let's do 17. Okay, let's see which one of these. Oh, here's one. Sorry, being indecisive over here. Not that one, this one. Okay. All right. Go over here, hit this, share that, bam. Okay, there it is. There it is. Okay, considering, all right. Why don't you guys take a stab at that? Here, I'm gonna try something. Does anyone have issues with that poll? Why don't you take a stab at this? I'll give you a few minutes to do the calculation and then we'll talk about it afterwards. I'm thinking. Yeah. We can't see. Oh, okay. The pole's in the way. Never mind then. That was dumb. Oh. Just move it. Oh, you can move it yourself. Oh, okay. Okay, try it again. Sorry. All right. Sorry to whoever put their answer in. You have to put it in again. No, you're good. No problem. Yeah, I can reshare the link. Here you go. Yes, I will explain that. Yes, red cat, that is correct. Yeah. Okay. This is I'll give you another minute. So if you don't know, you don't know, you can go ahead and guess. We'll still talk about it. It's okay. It's just interesting to see what you guys will get. And I'm trying to, make sure it's just not me sitting here and talking for 2 hours. Ooh, we got a guess for E. Yes, get your guesses in. 10 seconds. It doesn't really matter actually if you guess or not, but I guess it's for bragging rights. Another answer for E. I wonder if people on YouTube, they probably can't see this, but who cares? Oh, let me start erasing my board. Should have been writing stuff down. Wasting time. Okay. Okay. So, oof. Excuse me. So the right answer, the answer I was looking for was B. Just so you know, we'll talk about it right now. Okay, get rid of this. So we have our two half reactions. So we have Ag plus. I don't care about states. E minus goes to Ag S. Okay, and then Cu 2 plus E 2E minus goes to a Cu solid. Okay, and this one has E naught 0.337. This one is 0, E naught 0.800. Okay, here we go. All right, so I wanted to know about what's the Eocell for this, and some of you probably ran into this problem. Is okay, I don't know which one I should, so both of those are reductions, so I don't know which one should be which. When it is written like this, how do you determine the cathode and anode? Exactly. Okay, so how I would do it is I would look at your Eocell equation. Okay, Eocell. Okay, naught equals my E cathode minus my E anode. Okay, and then I would also look at this one, delta G equals negative NF E, or delta G naught. So, okay. So when a question asks you about a voltaic cell of these two things, you should automatically, you want the spontaneous one. So you want the one that's spontaneous. Okay. All right, so we want the spontaneous one. So down here, delta G, I know delta G, it's spontaneous when delta G is negative. Okay, these two numbers are always positive, no matter what you do. Can't control it. Okay, so for this number to be negative, if I want this number to be negative, I need this number right here to be positive, right? If it was negative, right? If this was negative, then it would cancel out that and make that positive. All right, so I need my Eocell to be positive. That's the thing. I need Eocell greater than 0. Okay, this is a more complicated way. I don't know why I'm explaining it this way. There's another. Okay, so now I know that I need Eocell to be greater than 0, so I need the cathode, the one that's being reduced, to be greater than whatever the anode is. Okay. So I look up here and I see, oh, this one's bigger, so I need this one to be the cathode and this one to be the anode, right? So I get Eocell naught equals 0.800 minus 0.337, and you get the whatever it was, 4 point something something, right? Let me do it again, just in case I messed it up in the question. 0.463 volts. right? Is that the only way to know the cathode? No. So another thing you could do is you could just guess, be like, oh, I'm gonna guess that this one is the anode cathode. This one's the anode. And then when you do your math, you'll get the Eocell. Eocell naught is negative 0.463. And be like, oh wait, I want the positive one because that I need I need the cell that's going to be spontaneous, so I need the other one. So just flip the sign. Eocell naught equals, so flip the sign and flip your things. So in this one, my cathode is Cu, and my anode is Ag. And then this one, my cathode is Ag, and my anode is Cu. And did we just assume it needed to be spontaneous, or was it in the question? So it was kind of implied in the question. So when it said I skipped someone's question. I'm sorry. I'll come back. No, I want to do this. So it just said evolve. Oh, go away. A galvanic cell made of these two things, right? It's implying that it wants the one that's spontaneous, or the one where the cathode and anode are in the right spots. Yeah. And then I saw someone else's question. If both E's are positive, do we choose the more negative one? You won't get both E's as positive you won't get both as positive. You either get one as positive and one as negative. They won't both be positive or negative. Okay, hold on. There's a lot. How do we know? No, I answered that one. Is that the only way what you know? Is the bigger E always a cathode? In the spontaneous one, yes. If he gives you a reaction and tells you, give me the E cell for this reaction, always go with the reaction. If he doesn't give you a reaction and just says the galvanic cell of these two things, then you do something like this, where you make it spontaneous. So you know it needs to be spontaneous because it's a galvanic cell. Yeah, I'm assuming they told me it was a galvanic cell that was in the right direction, so I'm saying it needs to be spontaneous. And did we just answer that one? More negative one. So in this type of problem, you want E cell to always be positive, yes. Right, in this type where it's just like, hey, I'm putting these two things in a galvanic cell. What's my E cell? E cell should be positive because I want the spontaneous one. Unless he says different. But it's a positive one. They'll probably put something that where he implies it's spontaneous, I'm thinking. Because I think that's how the book, there's a question like this in the book, I think. Okay. Does it not matter where the position of the half reactions are on the chart? The chart has they're arranged in order of higher to lower reduction percentile. So this E value, this E, right, they're arranged the higher or lower. So the higher you are on that chart, the more likely you are to be reduced. The better of a reducing agent, I think it is. So it's also the position on the chart kind of does matter. It's kind of the same thing. It's the same thing I'm doing here that I did my reasoning here, where one had to be bigger than the other. It'd be like the same. One has to be higher than the other to be reduced, if that answers your question. How do we know if NF is always positive? Is that just something that he mentioned in class? Well, N is the number of transferred electrons, can never be negative. F is a constant, so they're just positive. It's kind of, they have to be positive. There's no way you can have a negative number of electrons transferred and F is a constant. Okay, did I get everyone? to answer everyone's questions. Let me put it in the chat again if I missed it. No, I'm not seeing anything. All right. Okay, sweet. I'm gonna stop sharing this so I don't show you all the answers. But I can't copy the link. Can you send it to me? Yeah. Okay. Yeah, I can. Yeah, no worries. What was I doing? Now let's do something with solubility. Okay. Yeah, just let me know. Oh wait. Okay. Another question. How do we know which one is spontaneous when they are both positive? So both of these are never going to be positive, right? One's going to be negative, the other is going to be positive. You can't have both of them be positive, right? If I had a difference between two numbers, a difference, right? Oh, wait. I need the link to, it won't let me copy it from the chat. Okay. I meant the EO that is given. Oh, wait. So this, I don't need those to be positive. Like these two being positive, well, I guess it kind of relates to spontaneity, but I'm not looking at these two when I'm concerned with spontaneity, right? I'm just concerned with if this is positive or negative. Does that answer your question? Right. This one, this difference right here is what I'm, okay, yeah. Yes, I'll get you all the link to sign in. Just remind me afterwards because, I forget. Okay, anything else? Nope, sweet. So we got some solubility going on here. Excuse me. Share this thing, my jigger. Share here. Bam. Where's my, here it is. KSP, got KSP going on. We'll talk about this one. I think it's worthy of talking. So we have FeOH3, this KSP is 1.10 times 10 to the negative 36. And then we're looking for solubility inside of where we have a pH of 10.50. Remember, everyone, molar solubility is the S. Molar solubility is our S. Okay. All right, hopefully you got that in some way, shape, or form. I wrote down the gist over here. Bam. Did I? Okay. All right, KSP, remember solubility stuff? The reaction we're dealing with right here is FeOH3 bad parentheses, solid right there, in equilibrium with its 2 ions. So Fe3 plus aqueous plus, and then I have 3 OHs, so 3 OH minus aqueous. Right, don't forget. Right, you need to balance this. You would have put if you just put OH minus. Just make sure you balance this before you do anything with it. Okay, we would do our ice table, ICE, and then that's solid. Don't care about this. All right, so here's where the fun begins. Okay, so normally, right, we would put zeros right there because there's nothing in there. Well, we can put that for iron. There's no iron in our solution that we can tell. But since we got this pH, we know that there's some of this H3O minus sitting in here. Okay, got some this H3O minus. Okay, so I need to figure out this concentration right there. So that's what we'll do. Nothing too crazy. We'll get POH first from our pH. So POH is going to be 3.5, maybe, hopefully. So we can get my concentration of OH minus. Let's see, do math. So to get rid of pH, you do 10 to the negative that. So 10 to the negative 3.5, which is, oh, can you send me? Yeah. Yes, yes I can. Okay, so I can, what was I doing? Oh, POH, or no, OH minus concentration. Sorry, lost my brain for a second there. Nothing new though. And I get 3.16 times 10 to the negative 10 to the negative 4. Okay, so that's what's going to go right here. Okay. Then we do our S's where we used to have X, so plus S plus S. And so we have S and then 3.16 times 10 to the negative 4 plus S. Okay. And so now we can write our equilibrium expression. So we have our KSP way up there. So KSP, which is our 1. Oh, good catch. Plus 3. I was making sure everyone's awake. I wasn't. I forgot. 3. Good call. Okay. 3S, yes, I see. I'm an idiot. 3S, shouldn't it be 3S? Yeah, yes. Would we ever do negative S? If for a negative S, if you had like something there. So if I had like a number, so 0.1, you might have to do your KQ comparison. Remember? K versus Q. And depending on the question, if so, and then if you, let's say you get the perfect storm, so you get K is greater than Q. Excuse me. Or no. Q, you want the other way. You want this way. You want to shift that way. If you get this, right, then you would have a negative S. I think there's some questions on the worksheet. I think I did them in a couple other videos where you do get a negative S right there. So if you get something like where K is less than Q, and then it would shift that way. No problem. Okay. Good catch. Good question. Okay. Okay, now we can do our KSP thing. So this is 0. Put it back. So KSP, so my 1.10 times 10 to the negative 36 equals S times my 3.16 times 10 to the negative 4 plus 3F cubed. Didn't forget it that time. Cubed. Okay. Again, I don't want to cube a thing. So I'm going to make my S is small assumption, right? That's 10 to the negative 36. That's 10 to the negative 4. So I'm going to assume that S is really small, whatever it is, so I can ignore it. You only ignore this one, right? Because this is being added to something. We have to keep this one into account. And also, we wouldn't be able to solve for anything if this one didn't exist. Okay. All right. So we can solve for S now. So my S is going to be 1.10 times 10 to the negative 36 divided by 1 or 3.16 times 10 to the negative 4 cubed. I'm sorry I missed it. Why did you cancel out 3S? Oh, I'm assuming that S is small. So this is my S is small. S is small assumption. S is small. Yeah, okay. And I got S to be 3.48 times 10 to the negative 26, or 49. Do you still have to cube what's left though? Yes, still cube it. The cube stays. This 3S goes away. That's correct. Still cube it. So that's what I got. So this is our molar solubility. Oh, units here are moles per liter. Why do you cube IR? Why do you cube it? Hold on. So remember, if I wrote my equilibrium thing, so if I wrote my equilibrium for this, this KSP equals, excuse me, my concentration of Fe3 plus, and then my concentration of OH minus, but cubed, since I have this 3 right there, cubed. Oh, why do you not take the cube root before you divide it? Well, this is not cubed. I'm solving for S. Oh, wait. Okay. I'm solving for S, so I don't want to take the cube root of it. If I did take, so if maybe you're thinking about, oh, just take the cube root and then you could just solve for that S and leave it in there. But I don't want to do that, because if I take the cube root of this, then I have S, the cube root of S I have to solve for too, which is not good. So that, So this is why I cube it. I don't want to take the cube root because of it, because I'm solving for just regular S, so I just divide it over. Cool. And then do we need to verify? Like, yeah, I still need to verify. You're right. I do need to verify it. So let's verify. So I take my 3.49 times 10 to the negative 26 over my 3.16 times 10 to the negative 4 times 100. I got something that was way less than 5%. Okay. So this is good. Check. You do still have to verify. If anytime you make this assumption, you do have to verify it with that. Questions? Anything else? So then we're done. We have our answer. That's the molar solubility right there. All right, did I miss anything? Nope. Any questions on this? So here I could do it if I had something. So if you have KSP, if you ever have like something like KSP equals 0.1 plus S times 0.1 plus S or something like that, right? If you have two of them, right, you don't do your S's small there, right? You would get rid of all your S's. I'm just trying to say we got fortunate that one of our S's was just by itself. So if you ever have a case where it's right here, like this, you have to solve that with your quadratic. Don't do your S's small. I think the worksheet problems are like this, where you end up with something like that, or maybe minuses there or something, but something like this, where if you tried to do S's small, you would get rid of all your S's and then you'd be done. Ooh, excuse me. Done with that. Okay. I don't see any other questions in the chat. I don't think anyone's raised their hands, so that's good. So what we got? Let's do. So we'll do this guy. Oh no, we already did one of those. Did that. Didn't do this. Oh, I'm not sharing it. That would be helpful if I did that. Here's the next one we're going to do. Here we go. Here we go. A lot of words. Ooh, my hips are hurting me. I'm going to erase this time. Okay, I'll write down. If okay. Alrighty, hopefully you wrote that. So go back over here. Wrote it, took a picture of it, did something. Oh wait, hold on. Oops. Forgot decimal point. Oops. Bam, done. All right, there you go. So those are our enthalpy values for the reaction. So we want to know when it goes from spontaneous to non-spontaneous. If remember, things from delta G is spontaneous when it's negative, non-spontaneous when it's positive. So it switches at 0. We did a kind of like this, right? 0 equals my our formula for delta G. G naught equals delta H minus T delta S. Okay. So I know these two numbers, right? So I put 0. Ooh, 290. Yeah, 289 or 298. Yes, you're right. So if I solve for T real fast, so I solve for T right there. So delta H over delta S, right? I need those to be in the same units. So negative 76 point, or negative 76 times 10 to the 3 joules per mole over negative 255 joules moles Kelvin. Okay, so my temperature is 298. Yes, someone said it. Not too bad. The hardest part is remembering this. This is what you're solving. Solving for this. Whatever. What about the units? I got 0.298. You forgot to put them in the same, like you forgot to put this one in joules and that one in kilojoules, maybe. Hold on, let me actually check my math. Oh, there's a chance. Oh, probably right. Probably wrote it wrong. Maybe I was the idiot that didn't do the thing. I got 298. So you have to put them, this one's in kilojoules, that one's in joules. They have to be in the, you left. You left it in kilojoules, I think. Okay, JK. Oh, okay, there we go. Alrighty. I thought it was 225. I was very confused. I got it just mixed up. Okay. All right. Oh, my computer's about to die. Okay, is everyone good now on this one? I just wanted to show it to you because it's like a problem we mentioned once and we may have forgotten about it. Okay, awesome. Or some people might have forgotten about it. So, okay, good. That was quick. Is there another one I want to talk about? There's one in chapter 16. Excuse me. So I don't know how many questions he's just going to pull straight from chapter 16, or is he going to try to mash 16 and 17 together, which he could. But this is a chapter 16 one. I want to remind you about. Okay. There you go. Sweet. So we have, what do we have? We want the pH of a 0.91 molar. Is chapter 19 on the exam? Yeah, up to, what is it? It's everything up to the Nernst equation. So like, the stuff where we started doing just regular Eocell, not Eocell not. 2 knots. But yes, chapter 19 is on the exam. It's calculating Eocell, we did earlier, calculating G from Eocell, K. I don't know. Actually, I don't know if K is going to be, if you need to be able to get from G Eocell to G naught to K. But yeah, all the stuff we talked about yesterday, so the concentration cells is not on there. So it gives you a KB. 5.6 times 10 to negative 4 of C2H5NH3. Okay, are you doing this? Do I need to? Do I need to work it, or all of you good? I guess I should have been asking that earlier because I was, working. Okay, that's what I was thinking. Okay, here it is. All right, going back. Right, so there's our thing. There's our KB. Come on, camera, thank you. So one thing we got to notice is that this breaks up. This is a salt. This would break up into C2H5NH3 plus I minus. All right, if we put this in water anyway. If we put it in water, I guess I should have said that C2H5NH3I aqueous goes to C2H5 NH3 plus I minus plus. Okay, and then we can all see, hopefully, that these are conjugate pairs, conjugate pair. All right, so we can get a pH from that. Okay, so I go right in my pH. This one has a KB, so this is a base, making that my acid. You could also look, this one has an extra H plus in that one, so that's why this one's an acid. Maybe that's how you think. I always like to look at KB or Ka because that tells me directly. So H5 NH3 plus my H2O. It's an acid, so I'm gonna get my C2H5NH2. Can we use Henderson-Hasselbalch? Ooh. Not in this case again, because I only have this guy floating in my solution. Right, I have 0 of that. And again, the math will show you that that equation becomes infinity, essentially. Infinity or undefined. Okay, plus my H3O plus. So if I was doing this, so this would be 0.91 molar. Don't care, that's water, my stable. That one don't care, that's water. This one's 0, that one's 0. So this 0 makes me so I can't use my Henderson-Hasselbalch. Okay. So then it's just our I-stable thing again. So I do my minus x plus x that you've seen 1,000 times plus x. Hopefully you're doing this. 0.91 minus x, x next. Bam. Okay. This is an acid, so I need my Ka, right? Because this is an acid. Again. Yeah, so I need Ka here. So Ka is 1.0, which is my Kw, times 10 to the negative 14 over what is, oh, the Kb up there, 5.6 times 10 to the negative 4. So my Ka is what? Something, some number. Hopefully I'll get it right. Oh, almost messed up. I'll put negative 4 instead of negative 14. Okay, oh jeez, so small. 1.8. So times 10 to the negative 11. Wait, is that not Henderson-Hasselbalch? It's not. I can't use Henderson-Hasselbalch here. But I do, so I would do the same thing if I was trying to do Henderson-Hasselbalch. I need a Ka, but I don't, I have a 0 right there. So this 0 is going to mess me up in my when you try to do your Henderson-Hasselbalch, because you won't have this base to put in there. Well, you will. It'll be 0, and your calculator won't be able to solve it. Either that or it's safe. If it's smart, it'll say it's infinity. But they'll probably just say it doesn't exist. Okay. Going back, that's 10 to the negative 11, 10 to the negative 1. So I can make my x small. So let's do that. So 1.8 times 10 to the negative 11 equals my x squared over 0.91 molar. So my x is going to be square root 4.03 times 10 to the negative 6. Oh, sorry. Started writing real small. Okay. We would check it. So do our 4.03 times 10 to the negative 6 over my initial, so 0.91 times 100. It's definitely less than 5%, so we're good. There. And finally, pH. Again, we have H3O plus, so I can just do my negative log of my x, which is 4.03 times 10 to the negative 6. And then my pH is negative log. This is 5.39. Bam. Bam. Yes. Yes. Questions? Right. Yes. Awesome. Couldn't you use Henderson-Hasselbalch with the equilibrium concentrations? Well, you don't know your equilibrium. The issue here is I don't know my equilibrium concentrations. Oh, wait, once I got my equilibrium concentrations, I guess you could, but what would be, I don't see the point. Like, you did all this work, you might as well just take the negative log of that. How do we know when pH is just the negative log versus when pH is 14 minus the negative log of the answer? So here, since I just have H3O plus, right, pH, you have to remember that pH, I'll do it in a different color. You got to remember that pH is the negative log of either H3O plus, it depends on how you write the equation, or pH is the negative log of H plus. The only difference is the difference between these two are how you work, right? However you write the equation. Okay. Okay. So in this case, we had the concentration. Oh, this is concentration. We had the concentration of our H3O plus. So I could just do the negative log here. But if it was a base, I would have OH minus right there, right? And so now I need to find POH first, POH, which is the negative log of my OH concentration. Getting cramped right there. And then I use my 14 minus POH equals pH. So it depends on what you have right here, right? What's your other part? You can also just say, look at this part, right? If it's an acid, you just take the negative log. If this is a base, then you need to do your 14 minus negative log. So when OH is in the equation, yeah, it involved 14, yeah. So when OH is right here, yeah. If this is OH, if OH just shows up in your equilibrium equation, then you do the 14 minus the negative log. If it doesn't, then you just do the negative log. Yeah. Yes. What is the difference between a question that uses the word titration in it versus the very first problem we did, if that makes sense? Well, the first problem we did was a titration problem because I'm putting, I don't think I specified on the first question that it was a titration, but it was. So let me go back and check. I did say it was titration. So yeah, it's titrated. So you said something. So work them the same. Got it. Yeah. If you're basic, so a titration is taking a base, like a known amount of a base or an acid, and adding in a known concentration of the other one at different volumes. So if you're mixing a acid and a base, so if the problem's like, oh, tell me the pH after I mix this much acid with this much base, then basically you're doing a titration problem. So it's all going to be the same. If that answers your question. Okay, all right. Okay, so I'll stop my talking, be done, because it's almost 10 o'clock. But I can still answer your questions if you have any. But if not, I'll be done and I'll post this to YouTube. I'll send the PowerPoint to everybody. And then you can, if you want to leave, you can always just leave and look at the PowerPoint later and as you would like to. No problem. No problem. Anytime, you guys. You're welcome. Thanks for coming. Thank you. No problem. Goat. Oh, wait. Before people leave, if you need me to send you the link, let me say it right now. So yeah. Okay, so I can remember. You're welcome, everyone. You're welcome. You're free to go also, unless you have any questions. No problem, everyone. Good luck in the test. I'll be sending out my meme for the people in the group me. Yes, I will be emailing you the Just Pretty game, Abby. Yeah, I'll give you the game. I need the link. Okay. Yes, I will get you the link. No problem. Yes. Yeah, I'll send you the link after everyone leaves, in case you're waiting on that. So we got a few people in here. I don't know if you have any questions or if you're just chilling. Or you need the link. Here, let me just send the link out now. Just needed it. Jason. need the link. Thank you. The link to Zach. I do. Navi. Patel. Yes, please. I need the link, Devin. Can you send me the link and group me because I still cannot copy the link? Yeah. Oh, you can still see that. That's fine. Group me. Oh, sorry, I forgot what I was doing. So I'll go here. Oh, I can go here. Sorry, I'm doing it right now. Ooh. Hold on, beeps. Hold on. Where's the link? Get share, export, copy link. Okay. I think I just sent it to Leia. Okay, who else needs it? Yes, Devin. Jason, can you send me the link to sign in? Yes, thank you, thanks. Good night, be safe. Thanks. Good. Thank you. Thanks for your help. Thank you. Thanks for the help. Thank you. Yes. Okay. Okay, no one's here.